Our next static equilibrium example deals with an object being loaded onto a truck at rest on a ramp that makes a 30-degree angle with the ground. Determine the normal and frictional forces measured in newtons being exerted by the object. So what's going on? So we've got a ramp, angle of 30 degrees. We've got a 100-kilogram object sitting on it. So what forces are acting on this? Well, we know from other things that we've done, we've got a force, we've got the weight of the object acts straight down. Gravity's going to pull that down. So we know we have weight, which is 100 kilograms times gravity, 9.81 meters per second squared. And it's all in the negative j direction. And so that works out. And now it talks about two other things. And one of them it talks about is the normal force. And so the normal force is the force of the ramp pushing back on the box. And it pushes back perpendicular to the ramp. In other words, no matter what angle the ramp is at, it pushes out of the ramp that way. You have the friction force, which is what is keeping it from falling down. That acts parallel to ramp. So it's what's keeping it there. So this is F. So if we draw this as a free body diagram, as we like to do with these statics problems, we've essentially got these three forces at play. And again, remember, we get to choose the origin, so we might as well choose something useful. So we're going to choose the origin to be where the box is. And so we know we've got the weight comes straight down. The friction one is easier to think about because we know it acts the same way as the ramp does. So this is F, and we know this is 30 degrees. The normal force, N, we know is perpendicular, which means this part must be 90 degrees. So this is a right angle. So then this entire part must be 90 plus 30, or 120 degrees in this case. Okay, so same thing is true for equilibrium. We know the sum of the forces in the x direction has to equal 0. So let's look at what's happening in the x direction. In the x direction, we have the part of F, so we have F times the cosine of 30 degrees, plus we have N. We said this angle is 120, so we have N times the cosine of 120 degrees. And we have nothing contributing from W, because it's all negative and in the y direction. So if we get out our calculator, cosine of 30 is 866, so 0.866 times F plus cosine of 120, for the N, so it's actually minus 0.5 times N. Those have to equal 0 because that's all of our forces acting in the x direction. We also know for equilibrium that the sum of the forces in the y direction has to equal 0. So what are our functions in the y directions? Well, for F, we have F times sine of 30 degrees. For N, we have N times the sine of 120 degrees. And for W, we know we're minus all of W. So with that, and that those added together have to equal 0. So sine of 30 is 0.5, so 0.5 times F plus sine of 120, which is 0.866, times N, minus, for W, we have that's 100 kilograms times the acceleration due to gravity, which we use 9.81. So it's 981 equals 0. Or if we want to rewrite that 0.5 F plus 0.866 times N is equal to 981. So again, we've seen before, this may actually be almost a perfect example of what we did in the past. Two equations, two unknowns. I think you even on one of the examples we had back then, you saw things that had these 0.866s, and you can see this is the type of place that these come from. When you've got 30-degree angles and those sorts of things, these things come up. So what way do we want to use to solve these? Well, we can use anything to solve it. The coefficients don't line up really well, so using adding them together may not be the best way to do it. I think one of the better ways to do that is because we only since we have the two variables with just a 0 over here, I think we can easily solve for one variable in terms of the other. So if we keep working with the sum of the forces in the x direction, we can rewrite that as 0.866 times F equals 0.5 times N. And then because it's easier, I'm going to multiply both sides by 2 and say that N equals 1. Make sure I get this right. 0.866 times 2, 1.732 times F. And then I'm going to substitute that way. So now I'm going to say 0.5 times F plus 0.866 times, instead of N, I'm going to have 1.732 times F equals 981. If I keep working with that, so if I take that 7.32 and multiply it by 0.866, I get 1.500 times F equals 981. And so I get that, add those together, 2 times F equals 981. So F must just equal whatever 981 divided by 2 is, which is 490.5 newtons. So that gives me one of them. And then I can bring this back this way. I know that N has to equal 1.732 times 490.5. So N must equal that times 1.732. I get 490.5. I'm sorry, 490.5 is F, sorry. It's the number I read. 849.5 newtons is this. And this is one of those weird things about using the same variables for units, or using variable names that are the same as the units. You get a little bit confused in here. Remember, this is friction. That's the normal force. N is the unit. So if it helps you, you want to use a different variable for N or for F, that's okay. Just make sure you've defined it well up top. Just in terms of check, we know that if we've drawn our arrows right, we should get positive numbers for both of those. And then if we really want to check this, we can always plug those back in and make sure everything works into all these subsets. But I'll leave that to you to do on your own time.